So this is not in your book. We're going to talk about statistics. So statistics, roughly speaking, is the science of learning from data. Mathematics is part of statistics, but there's a lot more involved besides just doing mathematical stuff. Data is numbers, but it's not just numbers. The numbers have a context. And where the numbers come from in statistics matters. Now here's an example. You've all known, like before an election, you hear polls. And typically the way pollsters work is they call people up. They call a sample, not the whole population, but just part of it. And they ask them who they'll vote for in an election. And then they use statistics to predict who the winner will be. Now, there are lots of potential flaws in polling. One possibility is people might not tell the truth. That's been a common issue in recent polls where people, instead of answering the question, honestly, they answer it the way they think they should. It may not change their vote, but that's a problem. Another problem with that is you're always polling before the election, and people sometimes change their mind. Sometimes things happen. If you don't poll the people randomly, that can affect things. I mean, if you could imagine, here's the United States, perfectly drawn. If you're trying to find out who's going to win an election, and then, here's like San Francisco. If you call a lot of people in San Francisco, but you forget to call people down here in Mississippi, it's not random. So you have to do it. You have to sample randomly. Now here's something that they've done work with to fix, but was a problem not so long ago. Usually they call people on the phone, but they would only call people on landlines. And people who own landlines tend to, I don't know, do you guys know what a landline is? Yeah, okay. This knowledge goes away after a while, but people didn't always have a phone attached to their head. People who use landlines tend to be older and therefore more conservative on average. So that data is not random. It can be skewed. There can be other problems too. You can do some statistical analysis and you can find things that seem connected, and then you scratch your head. So, as a famous example, if you know Philadelphia, I went to school in Philadelphia. If you track ice cream sales in Philadelphia and you track crime, there's ice cream sales and there's crime. They're correlated. When ice cream sales go up, crime goes up. When ice cream sales go down, crime goes down. And that suggests some kind of weird possibility. Do ice cream sales cause crime? Or does crime increase ice cream sales? And both of these seem pretty unlikely, but this correlation is true, but it's not really that hard to understand because both of these go up between, say, April and July during summer, where it gets hot. People buy more ice cream, and people are out, and there's more crime. This is what's called a hidden variable, or a confounding variable. when you find some kind of connection that doesn't, it's not really there. Say about variables. Oh, so one of the mantras of statisticians is correlation. I'm going to write this. Correlation is not causation. You have two things that seem to be connected statistically, but they're not causing each other. In this case, ice cream and crime are just caused by something else. If you take statistics, some of you are going to take statistics, you will learn a lot about polling, hidden and confounding variables, methodologies, and I'm not going to do that today. We're going to just look at some of the basic math behind statistics. In particular, something called descriptive statistics. Descriptive statistics allows you to characterize data based on its property. This is just the numerical properties. And there are 5 main categories that we're going to look at. Some of these will seem familiar to you right away. All right. First one is measures of frequency. So this involves just counting. So we're going to do a little descriptive counting here. We'll use the gender of students here as a variable. Students. So I'm going to do a quick statistical study here. I see 1, 2 males, 3 females, 1, 2, 3, 4, 5. That's so we see that in this class the frequency is for every 3 males there's 5 females. Now there's also something you could also look at. Who here has blue eyes? Anybody have blue eyes? 1. Just 1. So for every 8, there's just 1 blue-eyed person. That's another measure of frequency. So that's one of the categories. You just have some variable, you count it up. Second measure is measures of central tendency. Does anyone have any idea what that could be? Well, okay. So you might have run into these before. First one we're going to look at is median, which you also might know as average. Wait a minute. See, I'm following too carefully. The mean, which is the average, the median, and the mode. These are all measures of central tendency. So, as an example, I'm going to just write some scores. This could be like test scores. These are not real scores. They're made up, but okay, so I have these scores, and I hope everyone knows how I would find the average. Average. Yes?
Would you add them all up and divide them by the amount?
Okay, add them all up. And then you divide by how many there are. There's 2, 4, 6, 2, 4, 6, 8. So like 65 plus 70 plus 72 plus 74 plus 79, 83 plus 95 plus 100. Thank goodness for calculators. Okay, it's actually 80.33, 80 and a third. All right, this is a pretty good measure of where the middle of the data is. I gave a class a test and we came up with an average of 80. That's kind of a B average. That's not bad. Sometimes this is not a good measure of central tendency. Here's a statistic. In 2016, the average income in the U.S. was $46,500. Now, those of you who are aware of what goes on outside of the Bay Area would know this is a nice income. Around here, it doesn't get you as far. But all around the country, this is a really good income. But this doesn't really represent most people. The reason is because if you look at the way income is distributed, if you look at, say, income down here versus, dollars, how many dollars are involved, you see that while there are a lot of lower income people, they don't make much money. A lot of the money just goes to people who are very wealthy, a very small group. And this distorts this average. So instead, we sometimes look at the median, right? So, someone here know what the median is? Yes?
Isn't it the middle number?
It's the middle number. I'm going to kind of do a really hack. Okay, so here we have two middle numbers, 74 and 79. Does anyone know what you do to find the median when you have two numbers that are in the middle? Yeah.
You add them and then divide them by two.
Okay. Find their average, exactly. Yeah, so here, 153, so the average is 76.5. That's my median. Now you'll notice, remember the average was 80.33. But the median is 76.5. That's the guy in the middle. That actually tells me a little better. Half the students, were getting C's, right? So this is another measure of central tendency. Now, okay. So note that the measure of as a measure of center, median is more resistant to outliers. Outliers are, you have some kind of data that looks like this. You have all your data here, and then you have some guy out here or out here. Those are referred to as outliers. When you're a statistician, one of the things you have to evaluate is this like relevant? Is this meaningful data? Or is it just some kind of like an error in the data maybe. If you're doing an experiment, maybe you're measuring some property of something, and you washed your hands, you got some soap in the fluid, and it messed it up. So that's what an outlier is. It's just, you don't know. It could be valid data, may not. So let's see, median. So I'm going to put up a data set here. I don't really know what these numbers mean. It doesn't really matter. So the median here and the average happens to be 21. But we're interested in the mode. The mode is the data point that shows up the most, which in this case also happens to be 21. If we added a person like who's 100, that's going to change the median and the average quite a bit. But it's not going to change the mode. We still have more 21s than anything else. So as a way of like looking at data, if you have a particularly obvious mode, that may give you some information about the data. There's a picture of a bar graph here that I guess I'm just going to copy the bar graph onto like 3,000, 1,500, and 1, 3, 5, 6, 7. So this is what the bar graph looks like. Not very well drawn, but so the idea here is we've got this stretch of data, but you can tell right away that the average is not really, the median is not really what you want to look at. You want to look at this mode because the largest portion of the data is here. So that may tell you something about your data. All right. The next area, the next category, is one you may or may not have run into. These are in general called measures of dispersion or variation. Okay, I'll have to explain what that means. We have two common measures that we use. They're called, there's the range. That one you actually know. The variance. And there's one called standard deviation. Now, here the math actually gets a little complicated. I think you all know what the range means. If, as an example, the range for all people is from 0 to 122. If you look up on the web, the oldest person was this woman in France, died a few years ago. We think she was 122, but if you look at old people, the number of old people versus age, around 115, let's say this is like 100, kind of comes down rather steeply. Seems to kind of drop off right there. And she's out here at 122. This definitely was an outlier. Some people think this woman actually wasn't 122. They think she was impersonating her aunt. Maybe not. I mean, there weren't apparently good records, and you get a lot of attention being the oldest person in the world. Okay. At USF, the student range is, I'm told, around 16 to approximately 50. So ranges is a very rough measure of dispersion or variation. It tells you what range the possible data could be. As I said, the other measures, the math is a little more complicated. I'm just going to write the formula here for you and then see if I can explain it. Standard deviation is described as the square root of the sum of each data point minus, and this is a common statistical thing, x with a little bar over it means the average. So before you can compute the standard deviation, you need to compute the average. And then divided by how many. Sometimes we subtract 1, sometimes we don't. If n is large, it doesn't really matter. Yes. So we take the average, we subtract it from each item, which kind of centralizes the data, at 0. We add them all up, we find the average, and we find the square root. Okay, that's a standard deviation. The variance, which is, we use the Greek letter rho, is just s squared. So if I take away the square root sign, that's the variance. These numbers tell you how close the average data is, how close the data is to the average. So you might have two kind of sets of data with the same average. And one might look like this, where the data is all very close to the average. And here, the data is very spread out. So this would have a very large standard deviation, and this would have a very small standard deviation. So it kind of tells you, in some cases it's not relevant, but if you're doing some scientific experiment and you get a bunch of data, you'd rather have a small standard deviation. That tells you that whatever error is involved is smaller, whereas here, this kind of looks like something random is going on and you're not really getting good data. There's some rules about standard deviation. As long as your data set's reasonably large and distributed in an even manner, kind of a bell curve, if this is one standard deviation, if you look at all the data here, one standard deviation, that's 67% of your data. If you look at 2 standard deviations, let's color that a little differently, that's 94% of your data. So, standard deviation very regularly tells you how crowded in your data is to the center. Now, you might think, oh, my statistics class, am I going to have to calculate this? And the answer is no. We're going to use calculators. We have some time at the end. We'll actually give you a little practice. We got 2, 6, 8, 9. I've got a few calculators. A couple of you might have to double up. Okay, back to categories. There are measures of position. Okay. What does that mean? Well, here again, I'm gonna draw a table. Give you an idea what this means. Score, percentile. Probably all taken standardized tests and run into percentile. So here's 780 to 800. Here's the 99th percentile. 760, 780, 798, 780, 740, 760, 97, and so forth. All the way down to 1. These are SAT scores, and the way SAT scores work, they don't give you a score based on how many right, well, it's related to how many right or wrong you get, but they adjust your score so that this is always true. They norm the data, is what they call it. So if you scored 730, I guess that's here, 720 to 740. This is supposed to be, sorry, this is 95. This is 94. That means 5% of the people scored higher than you. So percentile is, this is the only measure of position we're going to talk about. Percentile. So it's just a feature of data that you might find interesting. Oh. That's really annoying. I tell you that there are 5 categories and my notes don't list 5. And as I said, this is not the subject I'm best at. Okay, so we're going to actually do something practical here. I have 6 calculators, so some of you will have to pair up, unless you have your own. Have a TI calculator? Okay, can you? We'll see how far they go. Oh, you have your own? Okay. Anybody else have their own? Yeah?
Thank you.
You guys are prepared.
Yes.
Please, is that going to do? Okay. It seems to have. Please be very careful. If I gave you one, please give it back. If I didn't give you one, keep it. They look the same, don't they? Okay. So, first thing we're going to do is well, you turn it on with the on switch. If you don't touch it for a while, it'll go off by itself and you just hit on again. You might want to hit the clear button to clear your screen. We're going to take a look. I'm going to put up some data values. So 1, 1, 2, 4, 5, 9, 12, 13, 14, 16, 17, 17. Okay, we'll start with that. So what you want to do is when you're in the blank screen, if you're not in the blank screen, you hit the second key and quit to go back to the blank screen. And you should look for a button that says Stat. Okay, everybody got that? Yeah, you see, your calculator will do.
You're supposed to bring up like a first variable, second variable like that?
See, I don't know how to use those calculators.
We can use the other ones.
Huh?
We could use the other ones.
Yeah, why don't you share this one? This will now take me a minute as I attempt to break into this brand new TI. And hope it works. So, okay, so if you press the Stat button, you should see an Edit button. And if you hit the Edit button, I can't see what it looks like right now, you should be able to enter the data. Hope you all know when you ever come to class for an exam with a calculator, you really want to bring extra batteries just in case your teacher doesn't bring extra batteries for you. All right, here we go. Stat, Edit, Enter. And you should see here 3 columns, L1, L2, L3. We're just going to use the L1 for now. And if you enter one of the numbers and then hit enter, it'll go into the list on L1. So I'm going to go ahead and do that. You should all try that. Well, 13. 14, 16, 17, 17. Okay. Is everyone caught up here? Okay. So now you want to press the Stat button again. And you go over to, you have to use the cursor to move over to Calc. And then you want to press 1 for 1 var stats. There are 2 variable stats that if we enter L1 and L2, but we're just going to do the 1 var stats. All right? So, now everybody tell me, do you see a list of information? You should see a list of information. First thing is X bar, which I told you is the average. On mine, it comes up 9.25. Does anyone have anything different? Does anyone have anything the same? Okay. Then you can see this symbol, sum of X equals 111. That's just, yes.
I got something different.
All right, let's take a look. Oh, well, close. So I might have entered the data wrong. Here, let's see. Edit. Okay, 11259. Let's see, you missed 4. Now, I have to tell you, I don't know how to. You could just add it at the bottom. Just go to the bottom and add 4. Yeah. Okay. There's a value here that's not that useful, but it's the sum of the squares, 471. And then you'll see Sx, I have 6.355. That's our standard deviation. And now I'm confused because here they list the variance as 6.08. I don't understand that. Oh, there's lots of other information. If you cursor down, you'll see min x equals 1. I don't know what Q1 is. You can take stats and come back and tell me what that means. MED, the median equals 10.5, which tells me already I've got an even number of numbers. It just picked the 2 middle ones and found the average. Max x is 17. That's obvious. Okay. So really handy. All I had to do is enter the data. Now, if you get to the point of doing some project in your stats class, or even better, you go on to a job, you'll get, data sets sent to you by the internet, and you'll use some stat package. I don't know what the popular one is today. What did we used to use? Well, there are these packages, and you just tell it, find the variance of this, find the average, find the mean. There are a lot of other tests that, these packages will do, which I'm going to just talk about very briefly. So, and as I said, my knowledge of this is, I'm not a stats professor. If you take stats, you're going to talk about some kind of, let's say an experiment you're going to do. And you get some, you get some data points. And, the data looks good. The data looks like your theory is correct, right? And you'll put your data points into the computer and you'll do some tests. Something called a t-test, something called a chi test. And I just want to mention what these tests are telling you. See, if you do an experiment and you're trying to show something's the case, your data might show that that's the case, but it might just show it accidentally. So, in general, what these tests are telling you is, what are the chances, you're hoping for like a 95%, 99%. And what these are telling you is, think, what are the chances that your data came out the way it did just randomly, right? So if you get a 99%, that means there's only a 1% chance that it was just kind of haphazard. That's pretty unlikely. This is, in some stat books, this is called the gold standard. It's really good. If you want to publish something, typically you're looking for 95%. Now here's something that's really creepy though. Let's say you go look at, you're a scientist and you look at some papers, and you look at 20 papers. And they all do some kind of statistical test and they're all 95%. Well, that sounds good, doesn't it? All pretty good experiments. 95% means 1 out of 20 is just random chance. That means there's a good chance one of these papers makes some, conclusion that's totally wrong. So statistics is not just math. It's it's taking math and understanding it. Again, we use these different measures of our data to get a feel for what it looks like. We do statistical tests to see if things correlate. Yes.
So like about the like measures of frequencies and stuff, like all this stuff, there, like, will that show up on the final, or is just this for like our stat class next semester?
Statistically speaking, there is 0 chance of them showing up on the final. Because we're just going over it today. There's no homework. There's nothing for you, right? Now, as a practical matter, I think that you probably should know mean, median, and mode from high school days, right?
Yeah, I remember that.
If you happen to know, have heard of standard deviation, or even can figure out how to do it on the calculator, you're a leg up. But it won't be on the exam, so.
Okay, thank
Okay.
you.
I'm glad we calmed your nerves on that.
Yeah.
There will be some calculus questions, but nobody can get those.
Yeah.
All right, any other questions? Okay, so I may say, this is kind of the end of the new learning period. It's been great having you all. Those of you